Alright, there we go. Okay, so the first easy thing is the probability of A or B if these things can't happen at the same time. Now, pretty much any questions we're going to give you, it's going to be things that can't happen at the same time. For example, it might be probability of, or you're looking at industrial accidents, and you might be asked what's the probability of 2 accidents or 3 accidents in the same year. Now, what I mean by is 2 accidents in the year or 3 accidents in the year. You can't have a year where you have 2 accidents and also 3 accidents. It'll be 0, 1, or 2, or 3, or 4 exclusively. Another example would be something like if you're asking for the probability of a king or a jack from a single card. There is no card, no funny business with wild cards, there's no card that's simultaneously a king and a jack. So any time that these things can't happen at the same time, mutually exclusive, the OR just means add. And this is going to be the case for the majority of the questions, the vast majority of the questions we ask you. The only kind of time when things can happen at the same time and you have to think a little bit more would be something like with rolling the dice. What is the probability of an odd number or a prime number? Because you can get an odd number and a prime number at the same time, and you have to think a little bit different. Or, for example, what's the probability of getting an odd number, or sorry, an even number or a 6 on a dice? This isn't going to be true because you can get an even number and a 6 is even as well. But in all those questions, you can just slow down and answer them easier than that. So, for example, what's the probability of even or 6 on a dice? How many ways can you get an even number or a 6?
4.
1 dice, 1,
3. A 2, a 4, a 6. See, that's included in that. So it'd be 3 out of 6. It's not equal to the probability of an even plus the probability of a 6, which would be a half plus a 6. But a harder example than that would be something like what's the probability of a king or a heart? Now you won't get one this hard, so it's not going to be probability of a king plus probability of a heart because you can get a king and a heart at the same time. Now, as I said, we're not going to give you one this hard, it'll be more this hard. So just to answer this one, I'm not recommending we do the big hard way, which I'm going to show next. We're just going to forget about that. You can actually figure these out. How many hearts have we got? 13. Ace to 10 and Jack, King, Queen. Now, you've got the 13 hearts here. How many more kings are there? 3. So you've got 16 out of 52, excuse me. That's not equal to 4 out of 52 plus 13 out of 52. So the OR means add when they can't happen at the same time, and that's going to happen pretty much for us all the time. So this is, I'll write mutually exclusive, means they can't happen at the same time. And as I said, it's going to be pretty much the case in all of the rest of our work. Okay. Now the harder example of that, when they can happen at the same time, you end up with the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B.
So that's when it can happen at the same time.
Yeah, this is the general thing. Now, I'm telling you, you won't need this. Okay? Basically, what this is, say for example, for the king or the hearts, so they can happen at the same time. So if you use that formula there, you'll get, what's the probability of the king?
13, yeah.
Very good, 1 out of 13 is very clever. I'm going to write it as 4 out of 52, 4 kings out of the deck. What's the probability of a heart? 13 out of 52. Now, what you have to do is you have to take away the probability of getting a card that is a king and a heart. How many cards are a king and a heart? 1, the king of hearts. So you take away the 1 out of 52. Now, the reason you take away the 1 out of 52 is this includes the king of hearts and this includes the king of hearts. So you counted the king of hearts twice, so you must take away 1. Okay? So here, this includes A and B. This includes A and B. So you've counted A and B twice, so you must take one of them away. Now I'm telling you not to be worrying about this. We won't need it. Any of the questions you have, you can just figure them out like we did the King of Hearts, just by counting. Okay. The second thing that we looked at, so the first one, this is easy, this will be pretty much the case all the time. The other scenario you have is the probability of A and B is equal to the probability of A multiplied by the probability of B. And this is when the two events are independent. Now, what independent means is if A happens or doesn't happen, it doesn't affect the probability of B happening. So, rolling a dice over here, taking a card over here, independent. Taking a card out of the deck, putting it in your pocket, and taking a second card out of your deck, well, getting a king on the first and the second are independent, because if you get a king the first time, it changes the probability of getting a king on the second card. Again, this is going to be the easy scenario, and most of the time, this is what you're going to be dealing with. I might just, so most of the time, or is just going to mean plus, and is going to mean multiply. Now, the other thing will just, I probably should have said, I said this is always true. If A and B can't happen at the same time, what's the probability of A and B?
They won't stop.
0. No, if A and B can't happen at the same time, what's the probability of A and B? 0. So when they're mutually exclusive, this is 0 and you just get this formula here. Okay. Now the slightly harder way of doing this, again, in specific questions, you'll be able to get away with it just by counting everything. But we are going to use the harder example of this to come up with a formula, and a formula that we're going to use in these tree diagrams. So what we're looking at, and let me explain the kind of questions we're going to answer. We're going to answer questions like, say you've got two types of people, well, let's say smokers and non-smokers, and let's say you've got some smokers get the lung disease, some smokers don't get the lung disease, some non-smokers get the lung disease, some non-smokers don't get the lung disease, and you're asking a question like, given that you know something is true, given some information, for example, given that someone has the lung disease, what is the probability that they're a smoker? And we're going to be calculating these probabilities in this section here. So this is for independent. The general thing is, and I'm going to write it slightly differently just so I get a nice little formula. I'm going to write the probability of B and A. Now this is if they're not independent. So this is the general formula. Now this, we're not going to use this. Most of the time things are going to be easy, or is going to mean plus, and is going to be multiply. We're going to just use this formula here to get a slightly different formula.
Well, we can say that's the same electronics.
This is going to be exactly the same. I'm going to have some truth table up here in a couple of pages. This is exactly, is it just you knows that?
No, we did it last year.
It's exactly the same stuff. Exactly the same. Okay? So this here, probability of B and A, well, that'll be the probability of B times the probability of A, given that you know B is true. Can I come up with, I can't necessarily convince you of that, apart from just maybe just doing an example here. So suppose we're taking two cards out of a deck. Well, first card, keeping it, taking out a second card, and suppose you're asking for the probability of an ace and an ace. So maybe I'll write this even slightly, a bit more notation. What's the probability that the first card is an ace and, do you ever write those ands like that in that Boolean algebra?
No.
You just, okay.
Not that advanced.
And x2, the second card is also an ace. Okay, so we know how to answer this, and we'll just show underneath how this formula, when we answer this, is actually given by B. So we have, I think we did this last day, but no harm going over it again. What's the probability that the first card is an ace?
1 over 52. 4.
4 aces out of 52. And now, what's the probability that the second card is an ace?
3.
3 out of 51. And what this is, you see, this isn't the probability that you get an ace out when you pull a deck out. It's a bit different. So what you actually have here is, this is the probability of an ace times the probability that the second card is an ace, given that you know the first card is an ace. Like, notice you don't include the situation 4 out of 51. So this is only the probability if the first card is an ace. So what you have here is the probability of an ace and the probability of an ace on the second card, given that you know the first card is an ace. If the first card is an ace, this is the correct probability. So this does give you the right situation. Now, the thing that we're going to be interested in...
Sorry, there, I'm
yeah.
interrupting. That A / B, what does the line stand for?
Oh yeah, this is what we're going to do here. This is the probability that x2 is equal to an ace, the second card is an ace, given that this is true.
That.
Yeah, given that. So given that this is true, or that you know that this is true, or yeah.
Okay.
So we'll just write that here. So this A, B, this is the event A, given that B is true, or B happened. And we're going to be interested in these kind of events, as I said, stuff like what's the probability that someone is a smoker given that they have a lung disease. It also gets into false negatives and false positives. For example, if everyone here went for a screening for some kind of disease, you ask questions about what's the probability that you have the disease given that the test is positive. Funnily enough, for rare diseases, you could have tests where 95% of people who test positive actually don't have the disease. And those numbers are really, really weird, and they come out of this thing here. This is called Bayes' theorem when we finish this off. So you take this guy here and you divide both sides by the probability of B, and we've got a formula that we will be using, and it is not on the tables. The probability of A, given that B is true, is the probability of, so just dividing both sides now, probability of B and A is the same as probability of A and B, divided by the probability of B. So this will be used, this tree diagram crack is going to come up in question 1. Compulsory. They're not hard. Well, this is the hard part about it. We're going to set up these tree diagrams. These are going to be okay. There's going to be an easy question, a medium question which isn't hard, and this is arguably hard. Once you get your head around it, it's done. I have a day class, they're not great, and they were flying at it by the end of it. No, you're good.
Are they going to see it?
No, they're the same people I'm doing that.
That's the why, is it?
They aren't great. Look, they know they're not great either. Okay. No, I don't really like all my class. These guys are breaking my heart.
Many of them.
40. I'd only about 20 of them ever show up, to be honest with you. Right. Okay. So that is actually, we'll be answering that question pretty much. Right. So this is this tree. So what you're going to have is a branching off, and there's different questions you can ask. I might actually do the second question first, because this is only really asking one question. So we'll do the second question first, page 92. Okay. So you've got a scenario. Now this, again, this is the kind of questions we come up with, but I mean, you've got mobile phones. Here it could be buying measuring devices from a company, 3 different measuring, or maybe 3 different companies producing thermometers. And the question might be, you buy so many of the first type, so many of the second, so many of the third. A certain percentage of the first type are defective, a certain percentage of the second are defective, a certain percentage of the third are defective. You answer questions like, find the probability, well this is the easy one, find the probability that you that a random thermometer is from company A or company B. Find the probability that a thermometer chosen at random is defective. And then this is the harder question. A certain mobile, or say a certain thermometer, you have a defective thermometer, what is the probability that it came from company A? This kind of question. So you get a tree diagram, which is easy enough. Easy question, medium, harder, hard. And it's pretty much what you're going to get. Okay, so we start with a mobile phone. So you can draw a picture of a phone. And it branches 3 different ways. Samsung, Nokia, iPhone. This is connected with decision trees and stuff like that as well. So you can have a Samsung, you can have a Nokia, and you can have, I'm going to call an iPhone an IP. And then in turn, when you have a Samsung, it can be defective or not defective. So I'll run with defective, not defective. A Nokia can be defective or not defective. An iPhone can be defective or not defective. And what we're going to do is we're going to put probabilities on, I call them nodes and edges, I suppose. I know what they're supposed to be leaves. I know they're branches anyway, right? So you put probabilities on the branches. So what's the probability that a random phone is a Samsung?
1 3.
No.
Sorry. 25.
25%. Yeah, the situation gives it though.
Depends on the percentages, so.
Well, yeah. So this, yeah, basically it does. So basically, you've got a situation. You got CIT shop. It's flogging phones left, right, and centre apparently, and 25% of the phones they sell are Samsung. So if you've got a random phone, well, 1 in 4 of them are Samsung. The probability that you get Samsung is going to be 1 in 4, 25%. So the probability of a Samsung, 25%. Probability of a Nokia is going to be 35%. Probability of an iPhone is going to be 40%. Now, what we actually have on these they're not really so much probabilities as conditional probabilities. What is the probability of defective given that you have a Samsung? What's the probability of defective given that you have a Samsung?
0.135.
0.03. Where did you get that?
Sorry. I just halved the 25%.
Okay. Again, if there's 2 options, it doesn't mean it's 50-50.
Yeah.
So it's 3% of these are defective. How many are not defective? 97%. Given that you have a Nokia, what's the probability that it's defective? I think 0 is the real answer. Yeah. 1%. And so 99% not defective. And given that you have an iPhone, what's the probability that it's defective? 100%, 2%, and 98%. This question is probably a bit out of date, right? Okay. Now, you can kind of calculate probabilities now. For example, the probability that you're Samsung and not defective. Now it should be using it should be the probability that it's Samsung times the probability that it's not defective given that it's a Samsung. In other words, it should be 0.25 by 0.97. The probability of Nokia and defective would be 0.35 by 0.01, this kind of crack. So some of the questions are going to be very, very easy. Now I might just write up something. Occasionally in these you'll see these U's and N's. This is useful.
Why are you using 0.25 instead of just like writing 25%?
I would say, that, first of all, they're the same thing.
Yeah.
They're the same thing. So, first of all, I'll say they're the same thing. Proper, what's that to you?
5%.
What is a percent?
It's a portion of something, isn't it?
It's
100, right?
It's a fraction of 100.
Something divided by something.
a percentage.
Portion.
It's
a number.
It's 100.
It's actually a number. That's the proper way to think about percent. Everything that you had then was, if you talk about 25% of, that's 25% multiplied by. And say if you've got 25%, really that's 25 by 1 over 100, which is 25 over 100, and then if you go into your essential maths or whatever, this is 0.25. The reason being, I don't want 25%. If I did 25% and 3%, this probability would be 75% squared, which is a mess. So I want it like that. Okay, but they are the same.
Yeah.
So I wouldn't put the percent, unless if you write the percent but then multiply them properly like this. So if you have the 20, as I said, if you 25% and 3%, 75% squared.